Hello, everybody, and welcome back. This is homework 941, actually. I should write it up here at the top. Homework, if I can write it, there we go. Homework 941, and this is going to be problem number 2, which has two parts, part A and part B. Okay, so we've got a seal here at some sort of amusement park or some sort of a Sea World, which doesn't seem to be in most people's good favor right now, but Sea World or whatever you want to call it, we've got a seal sliding down a ramp. All right, so here's our seal right there. Yep, that's my seal, and that's my seal right there at the bottom of the ramp. Okay, so let's see a little bit about the seal right here. What's going on with it? Well, it's got a mass of 42 kilograms. All right, mass equals 42 kilograms. Slides from rest, that's meaningful, right? So the initial velocity equals 0 meters per second. The top of the ramp is 1.7 meters higher, so that's 1.75 meters right there. What does that mean? Well, that's our h. That's our height h, so that's 1.75 meters. That's going to be meaningful because that's the height that the seal falls through. And our angle theta, that's, if I can get that crossed off there we go, equals 35 degrees. And lastly, the final speed of the seal before it hits the water is 4.4 meters per second. All right, so V final equals 4.40 meters per second. All right, well, this is the part of the chapter where we've been talking about non-conservative work that is done. All right, and we talked about how let's see here. I'll make this green. Actually, I'm going to write this for a second. Energy final equals energy initial. We talked about how that is conservation of energy, right? What you start with, what you finish up with is what you started with, and vice versa. All right. Everything's accounted for. There's no loss of energy. However, now we're going to be introducing energy final and energy initial and lost. Or you might say non-conservative work that is done. All right, so I'm going to call this energy initial right here in green, like green for go. Energy final, I'm going to make that in red right there. And we see here that friction is taking place. Friction is taking place, so we know that there's going to be a loss of energy in the system. All right, so I'm going to call this non-conservative work that takes place as the seal is sliding down. Okay? So what's our working equation right here? Our working equation is not energy final equals energy initial. That doesn't apply anymore because we have a loss of work, but we can say that energy final equals, I'll make this in green, energy initial plus this non-conservative work that is done. Now that could be a positive or negative value. I'll erase that right there because I messed that up. Positive or negative value, in our case, non-conservative, it's going to be negative because we're talking about friction. All right, what's an example of a positive entity that puts non-conservative work into a system? Well, an engine. An engine would do that. It adds energy from outside the system. Well, we're not talking about an engine. We're talking about friction. And so friction is going to be a negative value that robs the system of energy. All right, so let's ask ourselves here, what kind of energy does the seal have at these various different points? All right, let's just, I'm going to start with final actually because I have it over here on the far right, far left. What kind of energy does the seal have right here? Well, it does not have any potential energy anymore. Why does it not have potential energy? Because this bottom level right here we can think of as being 0, being base level. All right, so it's got no potential energy because it's at the bottom of the slide. But what kind of energy does it have? It's got kinetic energy. It's got kinetic energy because the seal is moving. All right, so that's the kind of energy it has finally right here. Energy initial, what kind of energy does it have initially? Well, I'll tell you what kind of energy it does not have initially, and that is kinetic energy. Kinetic energy initial equals 0. Why is that? Because it's not moving at all. Just like at the very bottom right here, kinetic or potential energy final equals 0. All right, at the very top, it doesn't have any kinetic energy to start with because it's not moving, but it certainly does have potential energy at the top. How do we state potential energy? Potential energy initial. Well, I'll write that again in just a second. Plus this non-conservative work, that is friction. All right. Well, how do we write out our kinetic energy final and a potential energy initial right here? Well, we know how to write kinetic energy at any one point because that's 1/2 mv squared, right? V final squared, I should say. All right. How do we write potential energy initial or potential energy at any one point? Well, that's going to be mg times the height. All right, the height that it is moved against gravity. Now gravity is able to do work for you. All right, so it's got energy due to its position. And we have this non-conservative work that is done right here, plus this non-conservative work due to friction. All right, so that's what A is asking us for right here. What is the value of this amount of work? Well, let's solve for that and see what we get. So I hope the color coding has been helpful, but now I'm just going to go with black because I'm tired of changing colors. All right, so how do we get the non-conservative work all by itself right there? Well, we have to subtract this mgh over to that side. So it's going to be 1/2 mass times velocity final squared minus mgh equals the non-conservative work that is done by friction. All right, and I think if we predict right, we should be able to predict that this is going to come out to be a negative value because friction takes work out of the system. So I think we're going to find it to be negative, but let's just see what we get. Okay. Well, let's plug in our values right here and see what we have. 1/2. What's the mass? That is 42 kilograms. Velocity final. What is that? 4.4 meters per second. That value squared, right? 1/2 mv squared minus the mass, once again, 42 kilograms times 9.81 meters per second squared times the height h. That's 1.75 meters above the pool that the seal starts out with. Okay, so let's find out what that is. What does that come out to? Well, I don't know about you, but I get negative 314.5 joules. That's probably too many significant digits right there, but 315 joules. That's how much, and that's our answer for part A. All right, that's how much non-conservative work that friction does against the seal right there, or against whatever is sliding down the ramp right there. All right, so that is the non-conservative work. Now let's find the coefficient of kinetic friction between the seal and the ramp. All right, well, what is that? So we found out that it does have friction, and friction takes energy out of the system. Let's find out what that friction is right there. So we need to, well, let's write out just our working equation for the work that friction does. All right, work is force times distance, right? So non-conservative CNWNC, I meant to write. Work non-conservative equals force, you might say non-conservative work times, or non-conservative force times distance. All right, what is that force of friction? What is the force of friction? Well, we know that it is mu k, right, times what? Times the normal force, right? The normal force is the force, you might say the supporting force, that's normal right there, that is perpendicular to the force parallel. If you recall that from forces in inclined planes. So what is the force parallel? Well, that's going to be mg, that is the mass times gravity of the seal, times the cosine of the angle theta. All right, remember that? So force perpendicular, did I say parallel? I meant perpendicular, I'm sorry. Force parallel is straight down the ramp. We don't care about that. We care about the force perpendicular because that's the same thing. That's going to be the same thing as the normal force. So the force perpendicular is mg cosine theta. Force parallel is mg sine theta. All right. So we have our force right here. Here's our force, our non-conservative force. Now we need to know that distance. What's the distance? What is the distance that the seal moves down the ramp? What that will do is that'll enable us to solve for this coefficient of kinetic friction right there. Well, what is that distance? Well, we have an angle right here. In fact, I'll make this make a different color. There's our angle theta. Okay. We have an opposite side. We got 1.75, and we need to know this distance down the face of the ramp. That's the hypotenuse, right? So, opposite, hypotenuse, and an angle. Well, for distance d, which is really the hypotenuse, right? We can say the sine of an angle equals 1.75 meters over the hypotenuse, right? The hypotenuse is really the distance d that we want to solve for. So that means that our hypotenuse is going to be 1.75 over the sine of, that should be a theta right there, all right? 1.75 meters over the sine, what's that angle? 35 degrees. All right, what do we get? 1.75, oops, I put 17.5. 0.75 divided by the sine of 35, I get 3.05 meters. Good, that's helpful. That gives us the distance down the face of the ramp that the seal is sliding. So that is our distance d right there. So let's go ahead and write that in. 3.05 meters. Excellent. Now we're in good position to solve for our coefficient right here because we know what this non-conservative work right here is equal to. It's equal to that we just calculated, right? So if all that is going to be equal to negative 314.5 joules, let's just solve for that, that mu k. I'm just going to get rid of those minus signs right there because that one and that one cancel out. And so that's going to be 314.5 joules divided by mg cosine. I should just write them all. Mg cosine theta. What's the mass of the seal? That's 42 kilograms. G is 9.81 meters per second squared, and times a cosine of 35 degrees. Mg cosine theta times that distance, this right here, distance 3.05 meters. 3.05 meters. Did everybody get that? So we just took this and divided it down beneath this 314.5, and that's going to be equal to our coefficient of kinetic friction. So all we have to do is a little bit of math or calculating, and we should have our answer. What do we get? I get 0.305 joules. 0.305. No, I'm sorry, not joules. It's nothing, right? The coefficient is just a coefficient. It's just a value. It's just a multiplier. So that's our answer right there. So a little bit of trig, a little bit of conservation of energy, and a little bit of non-conservative work, and even some inclined planes as well. But this is all stuff that we've had before. So there you have it. That's homework 941, problem number 2.